So we're going to start with a quick warm-up and guided meditation. So the reason why we do this is because some of these topics in sustainability and sustainable development can seem really far away from us and really big context and ideas about the world. So I just wanted to start out with something that can kind of draw our focus in, and we can quiet our minds and really think about how energy kind of can impact our daily life. So if everybody feels comfortable where they're sitting, that's really good. If you can have your feet both on the ground and can just take some time to find a comfortable posture. And at this time too, if you would feel more comfortable not having your camera on because you don't want people watching you do this exercise, that's fine too. You can shut your camera off, but nobody's going to be watching you because we're all going to be focusing on ourselves right now. So once you find a comfortable position, I want you to all take a deep breath in through your nose and then let it out through your mouth. And then again, a deep breath in through your nose and then out again through your mouth. And now you can slowly start to blink your eyes closed and just try and quiet your mind as much as possible. Forget about things that were maybe worrying you throughout the day, things that are coming up that may be worrying you. Just kind of focus on what it feels like to be inside of your body and your own mind right now. Take another deep breath in through your nose. And then let it out again through your mouth. And while you're here, I want you to picture a bright, sunny day. You're outside. The rays of sun are coming on your face, and it's so warm. And I really want you to picture that energy of the sun and how it feels to be warmed up by that sun. And the sun is the most powerful source of energy that we experience in our natural habitats. So I really want you to picture how that energy really powers you and the planet, and just how strong that force is. And really internalize that in your body. It's not just even on your face anymore. You can feel it almost in the center of your stomach. It's so strong. And let that kind of radiate throughout your whole body, those rays and waves of energy. And now when you're out on that sunny day, you're passing by a flowing stream of water, and it's going over rocks and it's really rushing. And I want you to picture or pretend like you can hear that rushing water and how fast that water is moving. Can you picture that energy being harnessed, that moving water, and how strong that force of water can be? And now on that bright sunny day next to that water, you feel a breeze brush past your face. And maybe it's even stronger. It's a strong force of wind, and it's ruffling through your clothes and it's messing up your hair. And I want you to picture how that strong energy can affect your body too, how you can be pushed by a force of wind or a breeze. And just now quietly think about all those three forces of natural sources of energy: the sun and the water and wind. Take another deep breath in through your nose and out again through your mouth. And when you're ready, you can slowly blink your eyes open and kind of recollect yourself in the space that you're in. And we're going to get started with a discussion about energy.
Yes, so let's just talk about why that exercise is more than just a really relaxing thing to do on a Tuesday evening. So the reason that we had you all do that with us is because we want to understand energy sources, right? What is energy? And a really tangible way to understand that is to look within ourselves. So that's why we had you just do that exercise, because meditation is a form of energy. We're breathing in, we're breathing out. And we just want to take this into a larger discussion. So our first question is, what is energy? And if anyone has any ideas, like maybe you have an idea from that exercise that you want to voice, anything. What do you think energy is, just from your day-to-day life? And anyone is free to just call out. It doesn't have to be the right answer. There's no right answer. Just we're just trying to figure out places in our life that we see energy, such as what we just did right then. We can think about heat energy, turning the stove on. I don't know if any of the facilitators, let's see, sorry, I think someone raised their hand. If you want to just call out.
Darsh, you can go.
Yes, feel free to call out. Thank you.
Okay, I wanted to say energy is everywhere. It can't be created or destroyed, but can be transferred. Anything that is still or is moving or anything has energy.
Awesome. Yes, exactly. Does anyone
Has energy. Everything is energy.
Yeah, no, keep going. If you have more to say, please.
That's all.
I don't know if any of our facilitators want to add anything, but that sounds great.
We have a response in the chat box from Sven Fridor. Energy is the power of movement.
Oh, I love how that's worded. And potential for movement. Interesting. Yes. So we all have a understanding of energy. And going on from that, does anyone have any ideas? What is some evidence that shows us that energy is present? So, for example, do you think it's like when something moves? Does anyone have any ideas? Yes, Adash. Sorry, I'm not pronouncing it.
Well, then it's basically in anything, even if it's moving or if it's still, because anything that's still, it has energy that is making it still, and anything that's making that there's energy which just makes it move, like just how humans have energy so they can move and do like exercise.
That's awesome. Does anyone? Maybe we should talk a little about exercise and energy, because we just did a meditation exercise, which is a very calming form of exercise. Yes, great connection. Can anyone else think of a connection, like jumping jacks, anything like that?
Can I add on to what I said?
Yes, of course, please.
When we do meditation, there's always something going on in our body, like some energy in our body that's like cooling down, which makes us calm.
Yes, exactly. No, these are great. I see in the chat someone said one example could be solar energy. If you want to unmute and explain what you mean by that a little bit more, but yes, definitely solar energy. We're going to go into that later on.
A lot of types of energy.
I said that one example could be solar energy. For example, when you get energy from the sun, you could use solar panels to store that energy and use it to power objects.
Yes.
I have a comment about solar energy. I used a solar panel before, like just like a sample one. It could like just make like pencils move. It was attached to something which made the pencils move. So the energy, like there's potential, kinetic, and so many more. I can't remember.
Wow, you guys are experts. You know more than me. So we've discussed some evidence that shows us energy is present, such as we know that energy can be present even when things aren't moving, but we can see them when they are moving. And finally, not finally, but another question I have for the group is, what are the different forms of energy? So I have, I know there's mechanical.
Yeah, Nicole?
Nicole, sorry.
There could be like elastic energy, mechanical energy, kinetic energy, potential energy, and renewable energy.
Exactly, perfect. Do you want to explain for the group like any details about those?
So potential and kinetic energy both like work together. Potential energy is right before kinetic energy, and yeah.
Yeah, awesome. Let's see, some people are commenting in the chat. Magnetic energy, great. Gravity is energy. Yeah, maybe does Ella, do you want to unmute and talk about how solar energy is used by plants?
Yeah, I just think it's really interesting when a lot of us brought up solar and we kind of like, that was kind of the first part of the meditation. When we think about solar energy, like plants use it directly through photosynthesis, and from that we get then energy as humans from eating these plants that use the sun. And then also as humans, we can convert solar energy with solar panels, as I think Nicole mentioned, into electrical energy. So it's just really interesting to see both all the different types of energies, but also how they can be converted into different things and how we use them in different ways as humans.
Exactly, yes. Sorry, Ardash, so do you mind saying how you pronounce your name one more time? I see your hand is raised.
Adarsh.
Ardash, okay, perfect. What do you want to add here?
Yeah, I just wanted to say energy is related to fossil fuels because the energy is helping like flights and cars move, and then we need like coal and those types of things to make everything move. So they like energy and like fossil fuels work together to help things move.
Yeah, I think you know exactly the next question I'm going to ask, which is I was wondering if anyone wants to give an example of both a renewable energy source and a non-renewable energy source. So fossil fuels, you just mentioned one really big example of non-renewable energy. Does anyone want to dive into that a little deeper? Nicole?
An example of renewable energy could be hydroelectricity, because you use water, the movement of the water, to create energy. Well, not create energy, but to harness the energy.
Yeah, exactly. That's a really great new renewable source of energy. Anyone else have some? We talked about solar energy, which we focused on in our meditation. Anyone else? Just unmute, jump in.
I actually have a set which uses hydroelectricity. I forgot what it was, but it's something that like spins around. I forgot what it was called. It like spins around and helps the turbine spin to make like an electric thing. I used that thing, like a fake of that thing, and then I made the turbines move to, and then I had like a small light and I attached it to the light, so the light started to turn on when I
Cool.
started the motor.
Nicole, do you have a response? Do you think you know what that is?
Yes, I think you might be talking about a generator.
Like a specific type of generator where you like put water so it spins.
Maybe like a mini version of hydroelectric?
Well, I mean, you use hydroelectricity, but I don't know what it was called.
Wow, that sounds really interesting. I haven't heard of many versions of renewable energy, but that's great. There are a lot of good comments in the chat. Solar, geothermal, nuclear. Jeremy, if you want to talk about nuclear energy, I see you have a comment.
Yeah, I think just going back to like connecting how we talked about the different types of energy in physics and then these different sources of electricity, I think it's really interesting just to make the connections. And one type that we haven't talked about directly, but I think is really important, is thermal energy. So when we talk about fossil fuels, thermal means heat, so it's energy from heat. So fossil fuels is burning pretty much anything, and that's what makes thermal energy. But nuclear energy works differently. Some of you might know this already, but it has to do with within the atom. So we're not heating something, it's using the nuclear reaction with that. So I think it's really interesting is to look at the different categories of energy. So we have fossil fuels, which are sort of the thermal energy. That's like you're burning wood, coal, oil, gas. Then you have nuclear energy, which is sort of at the atom level. And then, as was just said, was light energy, so solar energy, which sort of works in a very different way. And it's really cool because it's kind of like this third very different way of using energy. And I think it's really important to tie it back to those physics concepts that we talked about earlier, to see how they're all related. But I think great examples so far. Yeah. Any
Yeah.
other?
Everyone seems to be energy experts here. As Jeremy said, any other last ideas of renewable or non-renewable resources? Light? Yeah, light. So I would think solar and light, like getting energy from the sun's energy.
Geothermal as well is a useful energy source.
Yeah, do you want to talk a little bit more about geothermal, like exactly what that process is?
So geothermal is essentially basically what it sounds like. It's the Earth's crust and the mantle layer beneath that is very hot. So there's places where we can get energy from that when it's further, when it's closer to the surface of the Earth's crust. So in places where they have a lot of hot springs, like plate boundaries, that type of thing, they use geothermal energy.
Yeah, awesome. Yes, all great answers. And in the chat, we see hydrothermal energy as renewable. I think everyone here has a really good grasp on renewable and non-renewable. Just to say one more time, non-renewable would be nuclear and fossil fuels, things that the Earth can't produce in time to catch up with our demand of it. So unless anyone has any last thoughts on this, and feel free to just jump in, I'm going to pass this on to one of the other facilitators to go into the next exercise.
One thing I can say about, I think Gino's comment about light is that light is electromagnetic energy, and the visible light that we see is only a very small part of the spectrum of light. So for instance, like radiation coming from the sun comes in a lot of wavelengths that we can only see a very small part of, but that's definitely a great example. And also light, so like if you think about something being hot, like hot things glow usually. Like if you think about like a coal burning or like in your oven, like you can see the metal conduction plates glowing, and that's kind of, it shows how like the brighter things are translates into being hotter, which translates into thermal energy.
Awesome. Thank you everyone for that great discussion. Whoever is on for the next thing, feel free to jump in.
Sure. This slide is just really meant to give you a very global view on our discussion about energy. It sounds like everyone joining this call really has a good grasp of all the different kinds of energy and the types of energy that are more environment friendly. But just to keep in mind that there are about 7.8 people, world population. Each person is consuming energy, producing energy, as individuals, but also collectively, all of our industries, when we're in schools, businesses, we're all consuming and using energy. And here's just a quick figure for you. The global average carbon emissions are 36 billion tons per year. I know that number, it's very hard to grasp, but just think of it as the global average for a carbon footprint is 5 tons for an individual. Now, if we don't want the Earth's temperature to further rise, which has huge implications on severe weather conditions, loss of biodiversity, a lot of things that we're seeing today, it needs to be less than 2 tons of carbon dioxide emissions per person per year. In a country like the US, it's actually currently at 16 tons per year. So you kind of get a sense for where we are and how much really needs to be done for all of us to collectively really work toward environment-friendly energy sources. So this was just a big view before going into an exercise.
All right, so I just want to thank everyone for that really great discussion first. It seems like you all know like what you're talking about. And so we'll just move into our activity for tonight, which will be a home energy audit. So the point of this activity is just to get you guys thinking about how we use energy in our homes and how we see energy being used. And so yeah, how do we use energy in our homes? Like, do you guys have any ideas? Just throw anything out in the chat, maybe. So some of the ideas that you guys brought up earlier, just anything that produces motion or heat or produces light, all these use energy. And the context that we see energy being used in our homes, usually using electrical energy, right? You have your outlets that you can like plug chargers or appliances into. And the way that we think about electrical energy is measured in watt hours. And so what that means is that we measure energy as power multiplied by time. So what does that mean? So if you think about electrical energy as like water traveling through a pipe, like a fire hose, like a more powerful hose will both like be carrying like more water or be carrying water like faster, right? And that's actually how we calculate watts, which we don't need to go into, but the way you would calculate wattage is voltage multiplied by amperage, which can be thought of as like the force of the electrical energy multiplied by the rate of the electrical energy. And so energy is the ability to exert that power over a certain amount of time, right? So you think about a battery, you have the ability to use some amount of power for, like your phone might be like 4 or 5 hours around that time. And so what a lot of people might overlook is that a lot of the appliances in our homes actually even continue to use energy even when they're turned off. We call this standby consumption or standby energy. So if you think about your microwave oven or just like your oven in general, if you have a clock, that clock, it's producing light, right? So that's energy that's being consumed even if you're not using the microwave or using the oven. And even things like your phone charger, even if it's not plugged into your phone, as long as it's plugged into an outlet, there's this thing called a transformer in your phone charger, and that slowly uses energy even when it's not plugged into your phone. And so while these standby energy uses might be small, they add up a lot, right? Because it's always running, always running. And if you look at the chart over here, we can see, like we were talking about, things that produce heat, like heating, water heater, things that produce motion, like your washer and dryer, things that produce light, like your TV, DVD, or cable boxes. Those all use electrical energy in our homes. So before we move to the next slide, do you guys have any questions or comments? Awesome, I'm just that good at explaining, right? Okay, so go to the next slide. This is just a chart showing you guys common wattages of common household appliances. And so the wattage of an appliance is just how much power that appliance needs to operate. So if you think about like your phone, that needs a lot less power to operate than, say, your computer, which is basically just like a bigger version of your phone, right? So I see a question in the chat. Can daily appliances run with natural energy? So I'm guessing when you're talking about natural energy, you're talking about like solar energy or wind energy. And so another idea that we talked about, right, is that energy can be converted and stored and that kind of stuff, right? So when we harvest these natural energies, like solar energy or wind energy, we convert them to electrical energy using a photovoltaic cell for solar energy, or like a wind turbine for wind energy. And so that's how we convert this natural energy that we find in our world into electrical energy that we can use. And I guess, like, if you think about in like the olden times when you had like windmills that would power like a mill that would mill flour, that's an example of harnessing natural energy like the wind and converting it into mechanical energy. And then so these days we're essentially doing the same thing, but instead of converting it into mechanical energy and using that to grind flour, seeds, or something like that, we use generators to turn that energy into electrical energy that gets fed into our electrical grid. And that's the same energy that you're using when you plug in something into a wall socket. Think about that. So if you have like any more questions about that, feel free to type in the chat or just ask. So if we go to the next slide. So basically the activity that we have for you guys today is a home energy audit. So the procedure you see on the slides there, and then we'll also have a copy of that on the sheets that you'll see once we break down to breakout rooms. And so we just want you to choose one room in your house that has appliances or just anything that uses energy. And then we want you to think about like how much energy that uses over the course of a day. And then ultimately we want you to like kind of quantify that or see that in real life, like how many jumping jacks did you need to power a toaster for a day or something like that. So we can break out into our breakout rooms right now.
Actually, I think we're gonna go ahead and do the activity as a whole group to keep us all together.
Cool.
So I will. Does everybody have the worksheet that we sent out earlier? I'm also going to share on my screen.
I also sent a Word document version in the chat.
I'll give you just one more second to try and pull that up. And if anybody's having any problems, just go ahead and unmute yourself and let us know. Can everybody see my screen right now and see the worksheet?
Yeah.
Okay.
I can see it.
So as David started to explain, we're going to be doing some of our own calculations of energy use in our homes. So you want to pick a room in your home for your audit. And if you want to move to that room so it's easier for you to take a look, you can do that too. You can move around. We're gonna spend a little bit of time doing this, so you don't need to be focused on the Zoom call completely. You'll be working a little bit individually, and we'll just be here to answer questions. So, or if you want to stay in the room that you're in and just visualize the room that you pick. And so you're going to determine the wattage for each of the powered appliances using the chart provided, which is on page 2. So you're going to write all those down in this chart here, which has your personal energy meter. Is that clear to everyone what we're going to do? Are there any questions? Cool.
Wait, what was the personal energy meter for?
So
yes, I can help you guys out and like walk you guys through it. Basically, the worksheet will have a list of appliances with like typical wattages, and also a couple links to websites that also have wattages for other appliances that might not show up on that list. And so if we look at the graph, if we look at our personal energy meter, we see we can make a list of appliances. And so you'll just copy down the amount of watts that uses while it's powered. and the number of watts that it uses on standby, if any. And then in the daily use section, just think about how many hours per day you'll be using that. So for example, in my room, I have these two lamps, I have a mini fridge, my computer, and so you can write down how many hours per day you use it. And to calculate your daily energy usage, we have that formula up top. So you just multiply the amount of power that it uses times the hours that you use it per day, and you add that, or you add the standby wattage multiplied by the standby time, which is just 24 hours minus the number of hours that you will be using it. And so you add those two numbers together, and that will be your on-power energy usage plus your standby energy usage. You'll get that in terms of watt hours per day. Because remember, we talked about how watt hours are a measure of energy. And so watt hours per day is just how much energy you use per day for that appliance. And then you can convert that to kilowatt hours per day really easily by just dividing it by 1,000. And so if you guys want, you can kind of visualize this by doing one jumping jack for every watt hour consumed by that appliance per day. And this number is actually a little misleading because in real life, 1 watt hour is actually more around 5 jumping jacks in terms of like real energy. The amount of calories that you'll burn doing 5 jumping jacks is roughly around 1 watt hour. So if you think about all the energy they use per day, that's thousands upon thousands of jumping jacks that you'll have to do to.
Yeah, how are you supposed to know how many jumping jacks?
So you'll just divide your daily energy usage in watt hours and divide that by 100.
Yeah. So what I recommend everyone does is first you pick an appliance. So like the computer that you're on, or if you're thinking of your kitchen, maybe your fridge, and then look up the watts for when it's on and for when it's on standby. And then you can start working on the calculations and we can help you with that. So I think the first step should just be pick your appliances and find the values from the table. And then we can go through and figure out the daily use, the daily energy, and then we can do the jumping jacks later if you have questions on how to convert those.
Wait, so we're supposed to do multiple appliances?
Yeah, so we said about 5 if you have 5 in your room. But appliances can be, your phone, laptop, lamp, toaster, so many things, TV.
Can it be your
But yeah, so try to think of the appliances, and then you can start doing the calculations if you know how to do them based on the chart. If not, we can sort of work on them together. I think that makes the most sense to do it that way.
I can try sharing my screen and like doing it for just my room, so we can get like a walkthrough of like an example.
Can I just get a thumbs up from everybody if they've started working on their first appliance maybe on that chart?
So just to go through my thought process, if I look around my room, I have a All right, so now that I have my appliances down, I can go on and look at how many watts they'll use on power using this chart or one of these links.
One thing to really emphasize in this is that, as you can see, like looking at the chart, is there's a lot of things that use energy that we don't notice. Like I don't think of like my water heater as something that uses energy because I don't see it, but it uses a lot of energy. And like your AC and your heat and just kind of obviously the electricity in the wall, like we know, we kind of are more aware of that in the devices that use it. But things that are in our home that use like the most energy, like often you don't really think about.
Oh, and then another thing to keep in mind for refrigerators, usually the wattage that you'll see, it's not on 24/7, right? So how your refrigerator works is that it will turn on for a little bit to keep everything cool, and then turn off and turn on and off throughout the day instead of being on 24/7. And you can hear that when you're like standing next to a refrigerator, and you'll hear it like humming, and it'll suddenly stop, stuff like that.
How are people doing? Do we need a few more minutes, or can you if you want to put in the chat how much time you need?
So when we think about things that use a lot of watts, they're usually, you see like heaters or ACs, things that produce heat energy, right? And so that's because like heat energy is actually a lot more dense than like motion, right? You think of like rubbing your hands together when you're cold, you have to rub it. That takes a lot more motion than just waving your hand around, right? And so you can kind of apply that same like line of thinking to different appliances that you find in your house.
Yeah, and those changes are something we're going to talk about later, and how us as individuals can and like kind of change how much energy we use in our homes and all that individual. We'll go into that discussion later, but that's a great thing that you did.
Yes.
But also this exercise is it's not too particular. We're just trying to get a general sense of how much energy we're using, because it's something that I don't think a lot of people think about.
Fun fact, when you buy a box of light bulbs, on the back there'll be like a little food chart, like calories for the lights, if you're ever curious.
So for the laptop, if you look at how I used it, I think that I use my laptop probably around like 6 hours per day. And so when it's on, I'll be using 150 watts. And so for my standby watts, I just used 15.
But how do you calculate the standby watts?
So 15, I just used the value that it said for sleep mode.
Oh, okay.
Mm-hmm.
This was definitely a great exercise because it has everyone very engaged and asking a lot of questions. So thank you.
And you're starting to look at things that you've never, like, you know, looking at your light bulbs, thinking about your laptop. Really good questions.
Does anybody want to share if they've been surprised by anything that they've found so far, that some appliance uses a lot more energy than expected or a lot less?
I have something to say.
Yeah, go ahead.
This light bulb says it's 17.5 watts.
Oh, so that's a lot lower than the estimate that was on our chart, right? Which
yeah,
60.
Yeah, so you can put that one down then.
Usually the lower wattage light bulbs, if you look around it, you can check if it says like LED or like AMOLED,
LED.
that kind of stuff. So usually your LED light bulbs.
If you can click the yes again if you finish, just so we can see again, that'd be great.
Yes, I really like the comment by Jem. I think that that's something that I do that I probably shouldn't. I keep my charger in all night, and that uses much more.
Yeah, like I'll leave my computer charging for hours after it's fully charged, which I'm sure wastes a ton of energy.
Yeah, it's also bad for your computer. It can wear it down.
I also learned that recently too.
You can see like how bright this really is.
Yes, it's very bright.
So I'm seeing that David, I think, he owes us 38 jumping jacks for all of the energy that he's used today. Does anybody have a bigger number that they could beat David, that they've spent more jumping jacks?
Also interesting to see if any of you were in your kitchens. I'm sure there's going to be a lot more. So if you open the fridge a lot more, obviously the fridge will heat up and it'll need to use more power to keep it cold. But your fridge has sensors in it that keep it at a specific temperature so that your food doesn't go bad. So that's why your parents might tell you in the summer. I know when I was little, I'd like to like hold the fridge open to like cool me down in the summer, but that uses a lot of energy.
Once you take the watts, you figure out how many hours a day you use it. Then you multiply that by the on power watts. And then you calculate the standby watts and times that by the rest of the hours in a day.
Just saying, I don't know what you just said.
So you're going to take the watts times the number of hours you use it in a day, okay? So you're going to multiply them together. And then you're going to add the standby time, which is when you're not using it, times the rest of the hours of a day. So let's say you have the refrigerator that you use for 3 hours a day. Like we said, that's the average. You would take the watts, which is 700, times the 3, and then you would add that to the standby, which is 50, times 21, because there's 21 other hours in a day. And then you add those two numbers together, and then you take that, and then you divide that by 1,000, and then you get the kilowatt hours per day. And then from that, you can get the jumping jacks.
Interrupt, but I know our facilitators also have some other slides you wanted to share with the group, and we're kind of getting close to time. So I don't want to discourage you from all of you from discontinuing this activity. Please continue, but maybe we can have the facilitators share some of the other information with us, and then we can either come back to it, or if you leave us with your email, we can send you a little bit extra instructions so you can continue this at home and maybe even talk to your parents and siblings about it as well. So maybe we just have a quick wrapping thoughts on the activity, and then go let the facilitators share their other slides as well. Thank you.
Yeah, so I think the real takeaway is just the longer you use an appliance for, the more energy it uses. And that's the really important part that we want to take away from this activity. So hopefully those who were able to do the calculations can see that. And for those who were a little confused, which is okay, you can talk about it later, maybe on your own with a grown-up. But I think you can also see David's example. So the ones that he uses longer end up using more energy. So that's really the big takeaway here. The longer something's plugged in, the longer you're using it, the more energy it uses. And I think that kind of makes sense. So maybe now we can move on to the next part. Yeah. So we just did all these fun calculations, but so what? We did all that. We figured out how much power it means. What does that mean? Now what do we do? So yeah. There we go. So now I just sort of want to take a step back, like we talked about before, and sort of explain, we just figured out how much power our room uses, right? Where does this come from? We talked about some of these sources before, but I wanted to make this more specific to the area that a lot of you live in. So for New York State, New York City, New Jersey, Pennsylvania, Connecticut, that whole area, all gets its power from the same 3 main resources. It gets it from natural gas or fracking. You may have heard that word used before. It comes from nuclear energy, and a small amount comes from hydroelectric energy. So we talked about at the beginning the difference between renewable and non-renewable sources. Oh, can we go back? Thanks. So who remembers which one of these sources is renewable? Who can tell me which one it is?
May I?
Yeah, sure.
Hydroelectricity.
Yes.
Because you can use the water over and over again.
Exactly. So renewable means we can keep on using it over and over again. So that's the small amount of where our power comes from in this area. Most of it comes from natural gas, which is a fossil fuel. And so like we talked about at the beginning, that comes from burning the gas. So here you can see this is where they get the gas from. They dig down in the ground, and they shoot water into the ground, and then the natural gas comes up. and that's how we get natural gas. So it's not the natural gas itself. That's a good question, Nicole, but it is when we burn it. So in order to get the energy, we have to burn it. Just like when you burn wood in a fireplace or charcoal if you're having a cookout, that smoke, what comes off of that is what causes global warming then. And we're going to talk more about that in a little bit. So if we can move on to the next slide. Yes, go ahead.
Actually, I have another question. If it's already a natural gas, doesn't that mean that it's already a gas? So how could you burn it?
So it's called natural gas, but it's actually a liquid. Think of like the gasoline in your car. It's not the same thing as the gasoline in your car, but it's a similar word that we use for that. So when it comes out of the ground in this form, it's usually in liquid form. But when it's a little complicated, but usually it's liquid, and so that's how you burn it. And you can still burn gases. If you ever turn on your stove, if you have a gas stove, that comes out as a gas, and you can still burn that. So you can still burn gases.
Can I say something about that, please?
Real quick.
Yeah, let's say you have a stove in your kitchen.
Mm-hmm.
That also uses gas, because when you turn it, but it doesn't light, you don't see anything come out. It's actually gas, because you can't see gas. So, but once a spark touches it or another flame, then it bursts into flames.
Yes, and that gas is the same gas that's the same thing as natural gas. Those are the same thing. For the most part, it's a little different, but pretty much that's the same thing. So why does this matter then? Why does it matter about fossil fuels? So it really has to do with what many of you may have heard about with global warming and greenhouse gases. And I won't get into the science right now because that's decently complicated, but basically when you burn these things, carbon dioxide goes up into the air and it traps the heat within the earth. And so that makes the temperature get warmer. And that has many issues, obviously, and we're going to talk more about that later. But what's really important, and the reason why we talked about electricity and the power in our homes is, as you can see, in the United States, 27% of our greenhouse gas comes from electricity. So that comes from the power plants that power our homes. That's a very big percentage. And you look at the other one is transportation. So I think earlier somebody asked about the cars. Why aren't we including cars? Cars emit so much more. Cars, buses, and planes, they have their own category. And you can see that here. So you can see how so much of the emissions is related to things that we use every day. Power in our home, the car that our parents may drive, the cars that some of you may drive if you're a bit older, if you've ever been in an airplane. So it's really important to be aware of that everything in your life can connect to this. And so that's really what we wanted to show today by looking at appliances in our home. So not only does it use all this electricity, but since most of our electricity comes from natural gas, it ends up being a pollutant and ends up contributing to global warming. So I know that was a lot right there. Are there any questions on this?
I just want to briefly clarify when you burn all these fossil fuels, so all fossil fuels contain carbon, and natural gas and oil and coal are all different forms of carbon. And so when you burn them, they react with the oxygen in the air, and then they create byproducts of water and carbon dioxide. And so the carbon dioxide is the greenhouse gas that then enters the atmosphere. And when it's in the atmosphere, solar energy that comes in normally would exit the atmosphere, which is how the atmosphere is really good at regulating temperature on Earth. But with this excess amount of gas in the atmosphere, it almost creates a blanket around the Earth, so that this radiation from the sun that's bouncing off the Earth, then instead of exiting back into space, stays in the atmosphere. And that's how this slow global warming effect is happening. Yeah, Darsh?
I just wanted to make a comment about like the greenhouse gases, like carbon dioxide and those things. If you ever been to a botanical garden, it feels really hot inside the house. So if I just wanted to let everybody know that it's actually the carbon dioxide. It's very heavy when you're at a botanical garden house, when you're looking inside.
So I can just comment on that. So that's where the greenhouse gas effect name comes from, because so if we think about greenhouse gases at botanical gardens, you're exactly right. These tropical plants need that to be surrounded by very warm temperatures because the natural environments are warm, or or if you have a greenhouse where you're growing plants, like the plants need to be in a warm environment. So a greenhouse works by trapping that heat by surrounding the plants so that no air from the outside can enter. So it keeps a warm environment. So that's where this effect comes from. It's not the carbon dioxide that's in an actual greenhouse, but that's where the name comes from.
Yeah. So I know, again, this was a lot. Are there any other questions? So again, the key takeaway here, I think, is to understand how much electricity and transportation have an impact on this, and the idea that the greenhouse gas basically traps the heat that normally would go off into space. It traps it and keeps it on Earth. I think those are the two main takeaways from this part. Are there any questions on either of those points? Awesome. So then one other thing I want to emphasize, and this is super important, and I really think a lot of people don't think this way, but it's super important. The problem is not individual. So it's not one person's fault. It's everyone together. It's not you yourself don't use 27% of the country's electricity. You yourself are not using that much electricity. At least I hope not. And so I think that's really important to remember, is everyone is in this together. So we call that a collective problem. It's a group problem. And that means we have to work together to fix it. We can't fix it on our own. And so on the next slide, I'm going to talk a bit more about some ways that we can help to think about how to fix this, because we presented this problem and we want to come up with some solutions. So the first solution is to teach others. And that's what we're doing here today. We're here to teach you guys to help you can better understand this. And hopefully you can then teach other people. If you have younger brothers or sisters, maybe you can teach some of your friends. Teaching goes such a long way, because if people don't understand that, their fridge is using so much power, their heat is using so much power, they might not realize that there even is a problem. So that's number one. And you guys are already here doing that, which is great. The next thing is, so you can advocate for a cleaner future. So that means a bunch of different things. Advocating means to use your voice. So one thing is, you can write a petition to people in politics to ask them for things that you want to be changed. Maybe you can petition them to make sure everyone uses those 17.5 LED light bulbs. That'd be a great thing to do. Or maybe you want them to have more awareness, just have the government do more awareness or do more on their end. Like maybe you want to ask the government to be like, hey, I don't want you to use natural gas anymore. I want you to use more solar. So that's a great thing that you can do. Even as a kid, you can totally write to your congressman. They love to hear from kids. The second one is, if it's safe and when it's safe again, you can join public marches. I was at the march in New York, and I think that's a great example of sharing your voice, because it's a collective problem, like I said. And so marching is a way to work collectively to try and fix that, because then everyone can see. Like you can see here in this picture, there are so many people in New York when that happened last year. And then all the news was there and everyone was talking about it. You may have heard about it. So I think that's a great way to do it. And then third, so many of you are probably on social media, on TikTok, Instagram, Snapchat. You can share some of the information that we did today on there, and just letting people know. I mean, heck, if you're playing Among Us in the group chat, why not explain a little bit about, hey, make sure your phone's not plugged in while you're playing Among Us. You gotta make sure you conserve energy.
What if you have low battery though? That's the
well, yes, that's different. But I mean, if you're overcharging, like we talked about.
Like if you have like 80-90%.
Exactly. And then another thing that I think is really important, especially for those who are more in high school, and as you get older in the future, is to really think about how to promote green policy. So you may have heard things like the Green New Deal, or actually the light bulb campaign, I think is a really interesting one. You can look that up online. That was a whole thing. But there are certain policies that get done. And I think promoting that and understanding when you hear these things, that this is what they're talking about. They're talking about changing to renewables, or they're talking about changing how we use stuff in our household. And again, when we do it through policy and government, that means everyone's working together. Because just because Orion changed his light bulbs to 17.5 LEDs, great, awesome. But if he's the only one that does it, we can't fix the problem. But if everyone changes their light bulbs, wow, that would be so many jumping jacks, so many kilowatts. We can make a really big difference. So that's really why we need to work together. And so that brings us to the third one. You guys are all students, and that's why you need to keep on learning more for yourself so you can make better decisions. And then again, you need to learn more yourself so you can teach others and so you can advocate. So you guys, again, like I said, you're already doing this step, you're already here, which is awesome. I'm so glad you guys are all here. You're educating yourself, making yourself smarter, more engaged citizens. And the last one is, you can take a simple action today. If your laptop is at 100%, you can unplug it right now. Next time you go to the store, be like, hey, Mom, can we get LED lights? They last longer and they use less electricity. Little things like that can make a difference. And if we all do it, we can make a really big difference. So I just wanted to sort of give these as some ideas that I've sort of thought of. And I guess sort of to end, we have a few minutes left. If you have any questions or any other ideas on how we can work together to fix this, I think that would be great. So I definitely, now that we've sort of talked about it, I'd just like to open it up to you guys for these last 2 minutes. Yeah. Any comments, any questions, any simple actions that anyone has an idea of?
Is it true that if you just like do the simple thing like, I have one question. Are you preserving like energy and like watts if you are having like an outlet plugged in, but then you're not, like, let's say you have a charger plugged in, like, like the 3 lines with the circle, if you plug that in, but you're not plugging it into your laptop, if you take it out, does it save watts?
So actually, like your chargers will even like use standby energy, even if they aren't plugged into your device.
Like if you plug it in like this, but you're not using the other end to put it into your laptop, then does it use?
And so so the reason why it actually uses energy is because it has these things called transformers in them, and that takes energy.
I'm going to show mine. You can see right here. If you have it, so yes, here we go. You can continue explaining. I just thought I'd show.
Yeah, so as long as it's plugged into the wall socket, so the thing you see in your wall, as long as it's plugged in there, even if it's not plugged into your laptop or your phone, it'll still be consuming a little bit of energy. And over time, since usually those are things that we just leave plugged into the wall, right? So if you think like the span of a year, that'll actually use a lot of watt hours, and it won't be like an insignificant amount.
Good point, because I should do that right now.
Yeah, and it like David said, it depends what it is. So like if it's a lamp, that doesn't really matter. But like a laptop, if it has that little box, that transformer, that does use electricity on its own. That was a great question. Any other questions or comments?
Commented, I just did that right now.
Awesome.
One thing also that's important to kind of realize is we were comparing all these different things that use different amounts of energy. So it's really great that we understand like the little things that are using energy that all kind of add up, but also thinking about, okay, how can I save energy in kind of bigger ways? Like, oh, do I need to have the heat on all day? Or can I instead put on a sweater and put on socks to stay warmer that way? Or do I need to use the oven for everything? Or could I cook something on the stove? Like there's I really like this exercise because it kind of just keeps us aware of how we're using energy in general. And as Jeremy said, we really need to kind of create a collective change, and no one's individual action alone is going to make a difference, but it's really important that we understand that kind of changing the way that we think about our energy usage because the United States per person uses the most energy of any other country. And that's like a really shocking thing. And I think that it's our responsibility as young people to really understand how we can kind of change our habits and change kind of the way that we think about using energy.
So I think we're at the end of our time for today, but I just want to thank you all so much for joining us and participating. I put on this last slide here, so if you all can see it, if you wanted to write down some of those websites or social media links again. And we'll all stay on for a few more minutes if anybody has any questions, but if not, thank you again.
I think this just has been super interesting. It had like I like the science element that went behind it, and then the actions and the behaviors. It doesn't have to be big. We can change small habits at home that can lead to a lot of big changes. So I thought it's very, very helpful. Thank you so much.
Bye. Thank you all for coming. Have a good Thanksgiving, everyone.